A fully loaded jet can weigh close to 200 tons. It meets the 150 miles per hour, still dropping toward the ground at hundreds of feet every minute. By any normal definition, that is a controlled crash. And yet, most of the time, the people inside barely feel it. Watch closely from a window seat, and you will see the whole gear leg telescope upward as the plane settles. That small movement is doing an enormous amount of work, and it comes from one of the most underrated pieces of engineering on the entire aircraft. It is tempting to think of landing gear as just wheels and struts, something to hold the plane up and let it roll. But its real job is far harder. In the 2 or 3 seconds of touchdown, it has to catch the entire weight of the aircraft, absorb the energy of that descent, and do it smoothly enough that nothing breaks and no one is hurt. It has to manage this on a gentle landing and on a hard one in the rain, in crosswinds, thousands of times for decades. To pull that off, engineers built a device that behaves like a spring and a shock absorber at the same time. It is called the oleo strut. Inside each main landing gear leg is a sealed cylinder, and inside that cylinder are 2 things: hydraulic oil and a charge of compressed nitrogen gas. The nitrogen acts like a spring. The oil acts like a brake on that spring. Separately, neither would work. A pure spring would just bounce the aircraft back into the air. A pure damper would be too stiff and would shatter under the load. Combined, they do something remarkable. Engineers call it an oleo-pneumatic strut, oleo for the oil, pneumatic for the gas, and nearly every airliner flying today lands on some version of it. When the wheels hit the runway, the strut begins to compress. As it does, the oil in the lower chamber is forced upward through a small, precisely sized hole called an orifice. Pushing thick fluid through a tiny opening takes force, and that resistance is exactly the point. It converts the violent kinetic energy of the descent into heat, which quietly dissipates away. At the same time, the oil pushing into the upper chamber squeezes the nitrogen, which pushes back harder and harder as it is compressed. So the deeper the strut sinks, the more it resists, catching the aircraft over a distance instead of in a single jolt. There is an even clever detail. The faster the strut is compressed, the more the oil resists because the damping force rises with the square of the speed. A gentle landing meets a gentle response. A hard landing meets a much firmer one. And running down the center of many struts is a tapered metering pin that changes the size of that orifice as the strut moves. It continuously tunes the resistance so the force on the airframe stays roughly constant, spread over the longest possible time. That is the secret to a landing that feels like a firm press rather than a hammer blow. Once the energy is absorbed, the strut wants to spring back, and an uncontrolled rebound could literally bounce the plane off the runway. So as the strut extends again, the oil is forced back through the orifice the other way, damping the recoil. The gear settles instead of bouncing. All of this happens in under a second, automatically, with no input from the pilots. The numbers these struts are built to handle are sobering. On a normal firm landing at maximum weight, the gear absorbs a descent of around 600 feet per minute. For certification, engineers have to prove it can survive an arrival at twice that, roughly 1,200 feet per minute without failing. That is a genuinely hard impact, and the gear is designed to take it and keep flying. To share that load, big jets use a lot of wheels. A Boeing 777 rolls on 12 main wheels. The A380 spreads its weight across 22. Each tire is inflated not with ordinary air but with nitrogen at pressures around 200 pounds per square inch, several times what a car tire holds, so it can carry tons without deforming. Not every leg carries the same load. The 2 big main gear assemblies, mounted under the wings and belly, take the vast majority of the weight and do almost all of the shock absorbing. The smaller nose gear up front carries only a fraction, steers the aircraft on the ground, and is deliberately kept lighter. That is why pilots hold the nose up for a moment after the main wheels touch, then lower it gently. Dropping the nose gear hard is one of the fastest ways to damage it, because it was never built to absorb the main impact. The strut is only part of the story. The instant the tires touch, they have to spin up from a standstill to over 150 miles per hour in a fraction of a second, which is why you sometimes see a puff of smoke. Then the brakes, the spoilers that pop up on the wings, and reverse thrust all work together to stop the aircraft. The brakes do their own energy conversion, turning motion into so much heat that the discs can glow. And after a heavy landing, they may need long minutes, sometimes cooling fans, before the aircraft can safely take off again. Here is the part that surprises people. The buttery smooth landing that passengers applaud is not always the safest one. On a wet or short runway, pilots are often trained to plant the aircraft firmly and deliberately. A firm touchdown puts the full weight on the wheels quickly, which helps the brakes bite and lets the grooved runway channel the water away. The landing gear is built precisely so that a firm arrival is never a problem. It is exactly what the strut was designed to swallow. So the next time you feel that solid thud beneath your seat, don't think of it as a rough landing. Think of it as a 200-ton machine being caught, cushioned, and stopped by a column of oil and gas the size of your leg, turning a violent arrival into a bump you will have forgotten by the time you reach the gate.